Here we go. So, yesterday we talked about two main arguments that we're going to use when we're trying to explain periodic trends on the periodic table. So, if I'm going across the periodic table, which argument am I going to use?
Number one,
the effective nuclear charge. There you go. So let's talk about the effective nuclear charge. As I go across the periodic table, the effective nuclear charge increases. So therefore, that means the nucleus becomes more positive, which means the electrons become more attracted to the nucleus. Yes? Yes. Those three things you got to remember. Okay? If I'm going down the periodic table, which argument do I use?
the distance.
The distance or the shielding. Okay? As I go down the periodic table, what am I adding?
You have the electrons.
Energy levels, right? I'm adding whole energy shells. So that means as I go down the periodic table, I'm adding whole energy levels. So the distance between my electrons and my nucleus is what? Increasing. So that means the attractive force between the nucleus and the electrons is decreasing, which means those electrons on the outer edge are held very loosely, and they're going to be easy to remove. Keep that in mind.
They're not very stiff.
Okay.
Wait, repeat something about that now. Wait, keep that in mind.
Keep in mind that the electrons on the edge are held very loosely, so therefore they're going to be easy to remove. You're welcome. Okay. Shielding. Okay, this is something else we can use when we're talking about going down the periodic table. Okay, this is where the inner electrons, okay, block the outer electrons from being able to feel the force, the attractive force of the nucleus.
Because there's so many of them? Or?
Yeah.
The repulsive force is strong.
Okay.
So like they just take up all the
Yeah.
charge?
Like, here's the nucleus, and then, like, here's these electrons, and then here's some more electrons. I know I'm drawing sloppy, I'm just doing it. And so by the time I start getting to out here, these electrons can't feel the nucleus as much because A, they're farther out, but B, also these negative electrons are shielding them from being able to feel that positive force. So it just pushes them out even further.
It's like the
So are you
repulsive
drawing
force is
like,
bigger
are you
than
drawing
the
that
attractive.
the big one as the third one, or there's other ones in there?
No, I'm drawing it as the third one.
Do they still have more energy than the one closer to the nucleus?
Yes.
Oh, that's cool.
Yes. As you go out, your electrons gain more energy.
Because you're not giving it to the nucleus.
Yes. Okay. All right.
Makes sense.
And then always remember this argument here, number 4, when we start trying to explain exceptions. Okay? Exceptions can normally be able to be explained with using number 4. Okay? Where we try to minimize electron-electron repulsions. Okay? To put the atom in a lower energy state and make it more stable. Okay? All right, we feel like we're reviewed up on it. We remember yesterday. We've jogged it fresh. All right. So let's start talking about the trends, okay, and how we explain them. Did we get here yesterday? No. Okay, so we're starting at the beginning. All right, so the first trend is atomic radius. So this is essentially, just think of atomic radius. I know it says radius. But just think of it as the size of the atom. Okay, so when you think of atomic radius, I just want you to think of this as size. Okay, so think of this as size of the atom. All right, as we go down the periodic table, okay, our atomic radius increases. Okay, what argument do we use when we're going down the periodic table?
Shielding or distance.
Shielding or distance. So let's start with distance. Distance needs to be your primary, okay? Shielding is what you can go to when you feel comfortable using it, but distance should be your primary, okay? So, as I go down the periodic table, what am I adding?
Adding more energy shells.
More energy shells. So as I add more energy shells, the distance between my electrons and the nucleus becomes what?
It increases.
It increases, okay? So therefore, what happens to the size of my radius?
It gets larger.
It gets bigger. Okay? Well, and you need to add in here because the attractive force between the nucleus and the electrons, what?
Is it
It gets weaker. That's all right here, sorry.
Could you say like
Okay,
the
so
repulsive force from the inner electrons is stronger than the attractive force?
I wouldn't,
No?
I wouldn't go there. I would just say as you add more energy levels, the distance between the nucleus and the electrons increases. So the attraction, right here, the attractive force the nucleus has on the electrons decreases. So then that means we're going to end up with a much larger radius. See that? Understand that? Okay. Now, as I go across the periodic table, my atomic radius decreases. Okay? What argument do we use when we talk about going across the periodic table?
Use
The effective nuclear charge. So as I go across the periodic table, the effective nuclear charge does what?
increases.
Increases. Okay? So the nucleus becomes more what? More positive, which means the electrons become more
Attracted to it.
attracted to the nucleus, so that's going to make the radius what?
Shrink.
Shrink. Do we see how we use these arguments? And we'll use them every single time.
Yeah, these would be for
So-
like a free response question.
Yes, these would be like a free response question, or they'll even do it for multiple choice. They'll just say, all right, here are these elements, like I think on your test it goes something like they give you W, X, Y, there's a Z, I forget how it goes. Anyway, there's elements that are in there, and there's just 6 of them arranged like that. And it says, okay, if this was a section off the periodic table, which of these atoms would be the smallest? Which would have the smallest radius?
and it gives us a picture.
And it gives you a picture. Okay? And so you would say, Y. Okay? Why is Y the smallest? Because as I go across the periodic table, my effective nuclear charge is increasing. My electrons are more strongly attracted, so we're coming in. As I go down, it gets bigger because I'm adding more energy levels. So that means that one would be the smallest one.
So if you say that as you go across the, what you call it, gets smaller and
You can't just say the trend.
yeah, that's what I'm saying. You have to like put in energy. with it.
Yes.
Okay.
All right, we feel comfortable with that one? Yes? All right, let's move on to number 2, ionization energy. Ionization energy is the energy required to remove an electron from an atom that's in a gas phase, okay? And I already know this is going to cost energy, okay? To remove an electron from an atom is going to cost me energy, okay? I'm going to have to use energy to get it out. Okay. Not only is it going to cost me energy, okay, if I tried to remove more electrons besides just one, each one of them is going to cost more energy than the one before it. Right? So let's think about this. Because you can use this, hint, hint, wink, wink, for our quiz tomorrow. Okay? You can use this to try to figure out, okay, what element they're talking about on the periodic table. Okay? So let's just say, for example, I'm going to tell you we're talking about magnesium. Okay? But how do I know I'm talking about magnesium? So I'm going to say, okay, well, magnesium's electron configuration is 1s2, 2s2, 2p6, 3s2. So how many valence electrons does magnesium have? 2, right? Because this is the first energy level. Here's the second energy level. This is the third energy level. So it's got 2 valence electrons. Okay. So let's say the first electron I remove costs me 700 kilojoules of energy. Okay. So now I'm at 3s1. Then I go back and I remove a second electron. Okay. So the amount of energy it takes to remove the second electron is going to go what? It's going to go up. It's going to take even more energy to remove this one. Let's just say 1600. I'm making up numbers, don't quote, okay? So let's say this one takes 1600. So now once I remove that second electron, I've completely removed the outer shell. So now if I try to remove a third electron, where am I going to have to take that electron from? from this 2p6, and that's one of the inner shell electrons, is it not? So this time, if I tried to remove that third electron, I would see this energy suddenly jump way up. Okay? You see how it pretty much doubled here? But then notice, what did it do between the second and third? You see how it jumped way up? So that's how you can look at ionization energies and kind of tell what you're working with. Okay? It's going to be easier to remove those valence electrons than it is to remove one from the inner shell. Yes, ma'am?
So it jumped because it like switched out shells and it's going from like
Yes. It jumped because these inner shells are going to be, these electrons are going to be more attracted to the nucleus. So it's going to be harder to remove those. Whereas those outer ones in the third energy level are farther away. They're not as attracted, easier to remove. You see that? Make sense?
So how can we tell that it's magnesium?
Well, I would just know it's got to be an element that has 2 valence electrons. Because it was easy to remove the first one. Double to remove the second one. It's about what I would expect. And then all of a sudden I got a huge increase in energy on the third. So that meant when I removed the third one, I was removing from the inner shell. So I knew there was 2 valence electrons.
So it wouldn't give you the 1s2, 2s2?
No, it would not give you that.
The 700.
It would just give you the 700, 1600, and 7000.
That makes sense.
All right, so let's talk about the trend with the ionization energy. Okay? As I go down the periodic table, okay, what do we know is happening as I go down the periodic table?
You get a bigger radius.
Okay, I'm adding energy levels, so the distance between my electrons and my nucleus is what?
Increasing.
Increasing, which means the attraction between my electrons and the nucleus is decreasing. Therefore, the amount of energy it's going to take to remove the electron is going to decrease. We see that? Make sense? Okay. All right.
So would you say like the... Okay, never mind.
It's not a dumb question. All right. Let's talk about what happens to the ionization energy as I go across the periodic table. As I go across the periodic table, what argument am I going to use?
The first one.
The effective nuclear charge. Okay, as I go across the periodic table, my effective nuclear charge is what?
Increasing.
Increasing, okay? Which means the nucleus is becoming more positive, which means the electrons are becoming more attracted. So what's going to happen to the amount of energy it takes to remove an electron? It's going to go up.
Would you have to say like because of the effective nuclear charge?
Yes.
Okay.
So when you go down, then the nucleus becomes less positive.
Yeah. Well, the nucleus doesn't become less positive. It's just the distance the electrons are from the nucleus increases. So remember when we talked about this equation yesterday? Okay. When my distance increases, what happens to this force here? It decreases. So your attractive force between your nucleus and your electrons are decreasing because they're so far away. We're good with this one? All right. Let's talk about a few exceptions right quick, all right, to ionization energy. Okay? So let's look at nitrogen versus oxygen. Okay? So before we even look at the exception, let's look about what we would say if we were looking on a periodic table. Okay? So we would say, okay, I see nitrogen, I see oxygen. Which one has the greater effective nuclear charge?
Just getting oxygen.
Oxygen, right? What happens as I go across the periodic table to my effective nuclear charge? It increases, okay? So nitrogen versus oxygen, who has the greater effective nuclear charge? Oxygen, okay? So who has the more positive nucleus? Oxygen. So whose electrons are more strongly attracted to the nucleus? Oxygen's. So who should require more energy to remove an electron? Oxygen. False.
What?
It's not a true statement. I can remove an electron easier from oxygen than I can from nitrogen, and it does not meet my rules. I just told you the argument you can use every time, and then I just told you is false.
You lied.
Here's the good thing, okay?
Just with oxygen.
On the periodic on the AP exam, they would tell you there's an exception, okay? They would say, here's the ionization energy for nitrogen, here's the ionization energy for oxygen, explain, okay? Why is it not meeting this? When you get stuck and you can't explain it, draw it. And then you should be able to see it, okay? You should be able to see it and understand it. So let's talk about nitrogen. When I draw out nitrogen, it's 1s2, 2s2, 2p3. Okay? So there's my nitrogen. When I draw out oxygen, it's 1s2, 2s2, 2p4. 1, 2, 3, 4.
Because it has a down arrow and so it's not stable. All right.
This right here, oxygen has a paired electrons in one of its suborbitals of the p orbital. Okay? Remember that fourth argument that I said you can use a lot of times to explain exceptions? All atoms want to minimize their electron-electron repulsions. Why? Because it puts them in a lower energy state and it makes them more stable. So oxygen is willing, okay, to give up this electron easier than, so this electron right here. Oxygen is more willing to give up than nitrogen is willing to give up that one because oxygen is trying to minimize the electron-electron repulsion.
So would it only be for like oxygen and
We're going to do another one and examples. So, because oxygen experiences more increased repulsion, it lowers the amount of energy required to remove that paired electron because oxygen wants to get to a lower, more stable energy state. I know it's a lot, but it does make sense.
it seems like
What
it's
about-
easy, but it's just like so much to take in. So I'm
Yes.
just like,
What about
Trying to
with
suck it
other
all in.
elements that are in oxygen, nitrogen, same situation? Could you
Like
do it with-
phosphorus and sulfur?
Yeah.
Same thing.
So same thing with all, like every single.
That's what-
Arsenic and
that's what I'm
selenium,
asking.
same thing. Antimony and tellurium,
So
however
if
you
it
say
did-
that, same thing.
What about oxygen like fluorine? Does that work the same way? Or is it,
No.
No, that would be regular same rule.
so
so that whole column 15 and 16,
Yes.
every single person in it.
Yes.
is it only 15 and 16, or could it be like?
Well, we're about to talk about one more.
Oh god.
Okay. All right. Now, also look at what happens, okay, between column 2 and column 3. And remember, we take out who when we talk about periodic trends? We take out those transition metals, okay?
That's what I was about to
So, here we've got from going from 2 to 3. Now, as I go across the periodic table, what happens to my effective nuclear charge? It increases. So the amount of energy it should take to remove an electron should also what? Increase. But if you look between 2 and 3, what do I notice?
I don't know.
What do I notice about the amount of energy it takes to remove an electron?
It goes down.
It decreases, okay? Even though the effective nuclear charge here is greater, just between these two, all the way down, I see a drop instead of an increase. That's because this is my S2 column, which means they all end in S2, and everything in this column ends in what? P1. Which one's closer to the nucleus? S2. That S energy level is closer to the nucleus. Okay? So, the fact that you're removing a P electron rather than an S electron, the P's are held less tightly because remember how we talked about who penetrates the nucleus more? The S, okay? Because P does not penetrate the nucleus as well as S, so it's easier to remove the P1 versus the S2.
Is that all?
Uh-huh.
Okay, good.
That's
So
all
all
the,
the exceptions are group 15, 16, and 2 and 13.
yes,
Okay.
those are your exceptions.
Okay.
Oh, that's great.
This class has been on it lately, and I'm just pumped about it. Okay? Pumped.
Act like it.
We've been doing great. We've been doing great.
Y'all have been doing great. All right, number 3. All right, electron affinity. Electron affinity is the opposite of ionization energy. Okay? So ionization energy is the amount of energy it takes to remove an electron. So electron affinity is the amount of energy it takes to
Yes,
add an electron. Okay? So, everything we just said about ionization energy with electron affinity is going to be the exact
Opposite.
opposite.
Okay.
So we're closer.
Okay.
To get to the nucleus.
Now, remember, if something is exothermic, what's going to be the sign of my energy change? Negative or positive? Negative. Okay? Remember, if something is exothermic, you see a negative sign on the energy change. Correct?
Correct.
Okay? And if something is endothermic, that means I did what?
You add.
I added energy, so my energy change is
Positive.
positive. Remember this? Okay? So here's how we're going to phrase this one. As I go down the periodic table, okay? As I go down the periodic table, what's happening to my distance? It becomes greater. So what happens to the attraction between my nucleus and my electrons? It decreases, which means what's going to happen to the amount of energy required to add an electron?
It's going to go down.
It's going to increase.
It's going to increase, okay? Because there's not a strong attraction between the nucleus and those distant electrons. So to get an electron to add in there and stay in there is going to take a lot of energy. Does that make sense? Because the electron's not attracted to the nucleus. So should I see a positive or a negative energy change with that? Did I have to add energy in to make the electron stay? Yes. So what kind of energy change should I expect with this? A very positive, right? It should be a very positive energy change, okay?
I just want to make sure I was right. Was that really?
Because that increased distance from the nucleus with the increasing energy levels means the nucleus is farther away from those valence electrons, which means it's harder to add an electron in there. Okay? Now, as I go across the periodic table, what's increasing? My ZIF, my effective nuclear charge, which means my nucleus is becoming more positive, which means my electrons are more attracted to the nucleus. So therefore, to add an electron would take what kind of energy? Less energy, right. Okay, so it would take less energy. So that means my energy change would be more negative.
Who named my kid that? Zeph.
ZIF.
My name is Zeph.
Now, of course, we always have exceptions. Okay? We always have exceptions. So let's talk about these. Okay? Let's talk about the fact that there is no such thing as a negative N, yet there is such a thing as a negative carbon. Okay? So that means, can I add an electron? Can I add one electron to nitrogen?
Yes.
No, because there's no such thing as N negative. Can I add an electron to carbon?
Yes.
Yes. Why? What do we do when we can't explain it?
Draw it.
Draw it.
Yay.
Okay? We don't quit. We draw it.
I said neglected. So
Okay.
I was right.
All right. So, N. Okay, let's look at nitrogen. It's 1s2, 2s2,
And then
2p, 1, 2, 3. Whereas we look at carbon. Carbon is 1s2, 2s2,
2p2.
and 2p, 1, 2. Why does there exist such a thing as C negative, but not such a thing as N negative?
Because you can
Because
take the
electron repulsion.
You add that
Yeah.
electron there.
Electron,
There you
electron
go.
repulsion.
If I add an electron to carbon, did I cause any electron-electron repulsion?
No.
No, I didn't. But if we come in here and try to add an electron to nitrogen, what did we just create there?
Okay.
Electron-electron repulsion, which would cause this atom to become more unstable. Do we become more unstable? No. The whole reason for bonding and adding electrons and all that is to become more stable. Okay? All right. Knowledge. You have a quiz tomorrow. I would really become very comfortable with ionization energy. That's what I would become comfortable with. Okay? All right.